Welcome, everybody. First of all, I would like to thank Krishna for accepting our invitation. It's a pleasure to have him here to open this new CosmoVerse series of seminars where we'll be discussing the tensions in cosmology, focusing on the new measurements and the proposed solutions. So for this reason, I invite you to join the working groups of CosmoVerse if you are interested. Okay, I'm sending now the link in the chat. Okay, so Krishna is currently a postdoctoral fellow in the Computational Cosmology Group at the Center of Theoretical Physics at the Polish Academy of Sciences. And prior to this, he earned his PhD from the University College of London under the supervision of Prof. Overlap. His main interests are the large-scale structure and the CMB's cross-correlation with voids and the role this plays in the CMB cold spot anomaly. And today he will present the dark matter solution to cosmic tensions and the ISW-void anomaly. Krishna, you can start when you're ready.
Okay, right. So thank you for the invitation. And so today what I'm going to be talking to you about is our recent publication. Okay, so this is a paper we've recently put on the archive. It's with these collaborators. So the basic idea is we're looking at whether dark matter can be the cause of the tensions and also specifically the ISW-void anomaly, which I'll get into. So I wanted to start with the standard model. So the standard model is what we use in cosmology. So it's made up of baryons, dark matter, and dark energy. I'm saying it's incomplete here because 95% of this model has yet to be measured. So dark matter is the CDM part of lambda CDM. This seeds structure formation, explains galaxy rotation curves, but it's not directly ever been observed yet. We still don't know what it is. There are some potential solutions, which include supersymmetric particles, axions, sterile neutrinos, but we really don't know if it's a single particle or many, and we don't know if it interacts. We know it certainly doesn't interact with radiation and matter very strongly, but does it interact with itself? Does it interact with dark energy? That's still unknown. In terms of dark energy, this has been brought about to explain the accelerated expansion of the universe. At the moment, it's seen to be a cosmological constant, which is a problem for theoretical physics. But it could also be telling us that our ideas of general relativity are not quite correct. So there are some other issues which I won't dwell on. So for example, what sets the initial conditions of our universe? Is inflation the right answer? There's also, is general relativity the correct framework to place our cosmological model in? So despite its incompleteness, lambda CDM has been really incredibly successful at describing cosmological observations. And tensions like the Hubble and sigma-8 tension are perhaps slight cracks in the model. So that's why they're extremely interesting to cosmologists. There's also other anomalies, which I'll get into. So the ISW-void anomaly is one. These are generally weaker and slightly lesser known. Okay, so what is the Hubble constant tension? Well, it's really a tension between inference of a Hubble constant value from the early universe, so from measurements of CMB and BAO, when compared to late universe measurements from Cepheids, for example. So at the moment, Planck measurements and CMB measurements seem to be going towards something like 67, but local measurements from Cepheids are around 73. And this is at the moment around about 5 or 4 sigma tension. The sigma 8 tension is the tension which comes from weak lensing measurements. So this is the famous banana from kids. And the green is from the kids' measurements, and Planck is the red here. And you can see that Planck actually prefers more clustering than what is generally seen from weak lensing measurements. This is not quite as high a significance as the Hubble tension. I think it's about 3 sigma. Okay, so the last few tensions which I talked about are very well known. Lesser known anomaly is the integrated Sachs-Wolfe Void anomaly. So before I get into what that is, I just wanted to describe the integrated Sachs-Wolfe first. So this is an effect which happens when photons from the CMB travel through potential wells which are evolving as the photons travel through it. So if you imagine a large overdensity here, a photon enters it, it gains energy as it comes into the potential well. But because this potential is decaying, it actually needs less energy to escape it. So the net result is that this photon gains a bit of energy, and it makes this region of the CMB look a little bit hotter. So there have been a lot of measurements over the years taking voids from photometric and spectroscopic surveys and looking at their imprint on the CMB. So what we tend to do is we find voids in these surveys, and we stack the ISW. So here is measurements from BOSS supervoids, and here is what we expect from theory and simulation. So if you look at the color bars, you can see that this is much, much larger than what we would expect. And here is a plot showing several measurements. So these measurements here are from photometric voids. And the reason I want to specify these are photometric is because photometric voids tend to be larger and also elongated along the line of sight. And this is just because the position of galaxies is not as well known radially. So you get this effect in photometric surveys where you can really pick out these sort of elongated voids along the line of sight. And if we look at the ISW, it's several factors larger than what we would expect from lambda CDM, which is 1 here. So there's also been measurements from spectroscopic voids, and these are much smaller and also spherical. And these are much closer to what we would expect from lambda CDM, but also slightly a bit larger. Okay, so let me go back. So when I talk about the integrated Sachs-Wolfe Void anomaly, this is what I'm talking about. It's this fact that we see much larger integrated Sachs-Wolfe from voids than what we would expect from lambda CDM. The measurements are not so, well, they're great, but they're not that precise. So they're in tension with lambda CDM at sort of a 2 sigma level. Okay, so related to this problem is the cold spot. So this is an anomaly which was found in the CMB, originally on WMAP, using something called a spherical mixing hat wavelet. And it was used to search for non-Gaussianities. And if you compare it just to the filter on the map, you find it to be a 4.5 sigma deviation. If you actually instead compare it to the colder spots in Gaussian realizations of CMB, it turns out to be a 2.5-ish sigma tension. Oh, sorry, not tension, a 2.5 sigma anomaly. We actually showed recently that if you take, yes,
Already one question if you,
sure.
okay, George.
Oh yeah, sorry. In your assessment of the integrated Sachs-Wolfe anomaly, what are you assuming about bias, etc., etc.?
So you mean the bias modeling?
Yeah, because you're using galaxies as your tracer of voids.
Yeah. So in the, it's a good question. So I actually haven't made the measurement myself. So the way this tends to be done is, I think the bias would probably come from clustering. I'm not certain though. Certainly in the simulations, this is just taken from a mock catalog. But yeah, it's, yeah, I need to look into it.
Okay.
Okay. So on the cold spot itself, if you actually take into effect the effect of masking, it turned out to be a sort of 1.9 sigma anomaly. So potential solution to this cold spot was that actually perhaps there was a very large void around redshift 1, and people went out to actually look for these voids, and they found some. So these are voids from a pencil beam survey in the cold spot direction. This is from a spectroscopic survey, and similar measurements have been made with photometric surveys. So this is from DES. And what we actually find is if you're trying to explain the full cold spot feature with just a void, this is actually a problem for lambda CDM, because the type of void you would need would be more problematic than actually the cold spot itself. So it's sort of not a good solution. However, in lambda CDM, you actually expect the cold spot to be aligned with voids anyway, and for the ISW to have a minor contribution to the cold spot feature. So far, it seems like the cold spot is perfectly consistent with lambda CDM. But if we take it in the context of the ISW-void anomaly, it might be another example of this effect. So while the void ISW signal seems much larger than what you would expect, the lensing seems to be the opposite. So this is lensing from DES. The blue error bars are from the data, and these measurements are from theory and simulations. And what you find, it's roughly a factor 0.85 what you would expect from lambda CDM. Of course, this assumes whatever rule profiles. A similar picture is seen for superclusters, and I think this is really effectively the same sigma rate effect being seen in another form. So what's responsible? So I've put this in big block capital letters. So I think systematics is clearly something that could be an issue, or perhaps incomplete theory. So I've got a few papers here which one talks on perhaps incomplete theory in the Hubble constant value, and something on the SA tension. Of course, this really needs to be looked at in great detail. But I think what most people want is actually, or what most people are hopeful for, is that this is actually evidence of maybe new physics. So if it is new physics, what is it? So there are several flavors of solutions to a Hubble tension. This is an incomplete list. So one solution is you have something before recombination, which increases the matter density. And this could maybe increase the Hubble value. But the problem with this is naturally, if you're increasing the matter density, you naturally increase sigma rate. So it's in tension, you solve one tension by making another tension worse. So it's not great in that context. Some of these models can be very exotic, and what I mean by this is you're invoking new physics where even in lambda CDM we have a lot of known unknowns, which I think we should maybe pay more attention to. There are other ways to look at this. So dynamical dark energy is also something which people look at, but it's recently been shown that if you want to solve both the Hubble and sigma ray tension, you need to cross the phantom divide. So what I've been thinking about is really if dark matter is a culprit. And the reason why I think dark matter is interesting in this context is because we often assume dark matter is very boring in lambda CDM. It just sits there, gravitates, helps all our galaxies come together. But other than that, it doesn't really do anything. But we've never observed it, so its physics is unknown. And it could be that dark matter is what's really the culprit behind these tensions. Also, another factor in this, in my thinking here, is that dark matter dominates most of the universe history. So if you're going to influence things like the Hubble constant and the sigma rate value, and it seems like a prime candidate. Of course, that comes with the other effect that because it dominates and it's so important to our picture of cosmology, it can't be a really significant change to lambda CDM, otherwise it'll really ruin things. And this is in contrast to lambda, which only starts to dominate relatively recently. So its influence in this context has to be very abrupt and quick. Okay, so what we've been looking at is what I'm calling evolving dark matter. And this is a subset of Wayne Hu's generalized dark matter model. So for simplicity, we are taking, we're basically saying that dark matter's equation state is non-zero. And we're not specifying why this is the case. We're just treating this completely phenomenologically. So for simplicity, we're just assuming that it's 0 at early times, and at some redshift, it starts to increase or decrease. And the reason we chose this model is because constraints on the dark matter equation state from C and B measurements are very consistent with 0. So it's unlikely that dark matter, at least at early times, has a non-zero equation state. And for simplicity, we've also assumed that this change occurs at redshift 1. Okay, so this affects how the matter density changes over time. So you now have this extra gamma term, which wasn't there in lambda CDM. And this describes the evolution in this evolving dark matter model. So we also get another term, which I will highlight later on, and this is this epsilon term. And this is a differential of the term above as a function of a logarithm of the scale factor. So in lambda CDM, the gamma term is 1 and epsilon is 0. Okay, so if we just set the early universe densities to Planck cosmology, we can play around with this model by fixing the Hubble constant value. So here is a model of evolving dark matter with the equation state changing as a function of the Hubble constant. So what you see is this results in much, if dark matter's equation state is negative, then we get an increase in the Hubble constant, and also a decrease in the amplitude of the power spectrum, which directly leads to sigma 8. So you naturally tie these two parameters together and these two tensions together. So in terms of the void ISW problem, I'm going to go through a bit more maps. So in terms of the lensing, we get this extra term gamma in the convergence. And for the ISW, which measures phi dot, then we get some extra terms here. So because matter has now an extra time component, you also need to include this in your functions. Right, so if we look at spectroscopic voids, what you find is this increases the ISW by about a factor of 1.8, which is consistent with what we find from observations. So the gray bands is the observations, and the purple is the amplitude increase from changing the Hubble value. For photometric voids, which are more elongated, this feature is enhanced, so you get a slightly larger increase, a factor of 2, which follows what we expect from, or what we see from observations. Although you can see the error bills are quite large. For the heterogeneous voids, which are the voids in front of a cold spot, we see a much larger increase. And this is really a specific example of what I would say photometric voids are. The lensing is also interesting in the sense that when we increase the Hubble value, we get a decrease in the Hubble, the lensing convergence profiles for these voids, which is exactly what we find in observations. So we're tying together the Hubble and sigma 8 tensions, and we also seem to be providing an explanation for the ISW and lensing from voids. So far, everything I've said has just been very simple. We're just fixing Planck densities at early times, and just seeing what happens if we treat the Hubble constant as a free parameter. Right, so if we actually constrain cosmological observations with this model, we find firstly, if we constrain with Planck, that we are really insensitive to this extra parameter in evolving dark matter. And this makes complete sense because by construction, the early universe part is completely kept the same. The only way this is being constrained is really through the sound horizon. If we include supernova from Pantheon and BO measurements from BOSS, this constrains the values closer to 0 for the equation of state. But if we include a prior on the Hubble constant from shoes, then we are pulled slightly away from 0 towards a non-zero value for the dark matter equation state. We focus now instead on the key parameters of Hubble constant sigma 8. You can see the same picture here. We'll pull towards lower values of sigma 8 and higher values of H0. What I would say in this model, the exchange between sigma 8 and the Hubble constant is quite steep. And what I mean by this is a little bit of change in the Hubble constant gives you quite a drastic change in sigma 8. So if you're trying to solve the tensions, you really want to lie somewhere here, and we seem to be lying more at this angle. which is why we don't really get towards the high values that we see from shoes. Okay, so the implications for dark sector physics. I think this is an interesting, I think the ISW from voids may be a smoking gun for a dark matter solution to tensions. And it can generally be used as a way to measure dark matter interactions, because then the way matter evolves through time is not just by AT to the cube, but you now have an extra time component. And this is maybe a way to measure this. So it opens a new path for testing dark matter physics. If it is what we seem to be finding, that it's non-zero, negative, and changing, this seems to be degenerate with interactive dark matter, dark energy models. If true, that would be really significant. And it will also mean dark energy is not a cosmological constant, so important. So in terms of lambda AeDM, as I'm calling it, I think the current measurements of void ISW and lensing have quite large error bars. So it's critical that we make these measurements more precise and we understand the void properties better. So understanding bias, etc. Future surveys like DESI, Euclid, and SST will really help us doing that. At the moment in our paper, we've limited the parameter space because I really wanted to focus on these effects. But you could consider other models, so including massive neutrinos. So the model is completely phenomenological. We haven't provided an explanation of why dark matter should behave this way. It would be interesting to find or to consider models which maybe could give rise to why this should occur. So that's something we'll be looking into. Okay, so thanks for listening. Yeah, thank you.
Okay, thanks a lot. Thank you for the very interesting talk. Do we have any questions?
Yes.
Yeah, please go ahead.
Yeah. Okay. So I mean, the way that this model behaves as you add different data sets, I think is very straightforward to understand. The things that what you're doing is you're trying to get this flick up in H0 at low redshifts, and the supernova data providing a strong constraint that limits what you can actually do. So what you get is, with the CMB, you get a degeneracy. You start breaking the degeneracy when you add BAO and supernova, and they don't want any additional parameters. You then add the H0 constraint, and that pulls you away from the lambda CDM solution a little bit, because you're now fighting against the rest of the data. And so you pull towards the shoes value, but your fit to this, particularly to the CMB, but your fits to the other data will be worse. And in the case of the CMB, they'll be actually unacceptable. So that's the first point. The second point is that on the sigma 8 tension, I don't think that it's it's enough to try and use this generalized model. The generalized model it's okay if you're dealing with the background evolution, but then for sigma 8 in your voids, you need to understand how perturbations evolve, and then that requires a knowledge or assumptions about the actual physics behind that generalized model. So for example, you could get something like what you want by having a subcomponent of a scalar field, some subset of the dark matter behaving like a scalar field with an equation of state that changes at late times. But then the actual nature is going to affect the perturbation. So I wasn't clear what assumptions you were making about the effective sound speed of the dark matter and how that alters perturbation growth.
Right, so we assume the sound speed is completely adiabatic. So there are some extra terms in the generalized dark matter model, viscosity, and also the effective sound speed, which we assume is just coming from adiabatic conditions. Otherwise, we just assume those are zero.
I mean, those are very specific assumptions. I mean, you can realize a similar background cosmology by having subsets of dark matter with different equations of state.
Right.
Any other questions? Yes.
Yes,
yeah.
I have one. If people can hear me,
Yes.
can I? Okay. So my question is, if you have a look at also to the consequences to small scale, it's related this question to the previous one. If you have some studied or investigated the effect of TS evolving that matter on small scale, say formation of galaxies and so on, so on.
So the answer is no. That's something which would be obviously very interesting to look into, but we have not looked into that yet.
But I think it will be very important, no, at the end, because I think that there is very likely it is related to the nature itself of the matter, no? Clearly.
Yeah.
And I think that could be important also to look this side of the effect.
Yeah,
Okay.
I completely agree.
Okay, thank you. Leandros?
Yes, thank you for the very nice talk. I'd like to point out that, in fact, the basic idea is to actually try to lower the growth rate of fluctuations using dark matter, while at the same time changing h of z. Now, the same combination of facts can be achieved with some simple modified gravity models where G effective is evolving. Have you looked at possible degeneracy between your approach and modified gravity approaches where G effective is changing, which actually would both affect the expansion rate and the growth rate of fluctuation?
No, I haven't. My understanding was that most modified gravity models, if you increase the Hubble constant value, tend to give you larger values of sigma rate, but maybe that's incorrect in this specific case. So yeah, that's something I can look into. Thanks.
Okay, thank you.
Any other questions? No, I have one. Why did you choose the redshift equal 1 and okay, that particular redshift? And did you check how changing this will affect your results?
Really, I chose it just to simplify simplify things, simplify the paper, because I really wanted to focus on how this affects these three components, the two tensions and also the ISW anomaly. So the other reason is because you don't want to make this change too early. Well, actually, that's probably not quite correct. Basically, it's something that can be changed, but
Yeah.
we haven't done it yet.
What about letting it free to vary and see if there is a preferred redshift?
Yeah, we could do that. The only thing I can think of is this. There might be some degeneracy with how lambda actually works. So I think you need to be a bit careful about how you treat it.
And I have also another question. Did you, check some if there is an improvement, like a model comparison with respect to the lambda dark matter model, with by evidence or just the chi-square?
I have those values, but I haven't looked at them yet.
Okay.
Can I ask a short question?
Yes.
Okay, very nice talk. My question is the following. Actually, it's twofold. The first is, does this consideration is this consideration in agreement with other characteristics of dark matter, for instance, with galaxy rotation curves or whatever? And the second is, can we have any information extraction about the nature of dark matter? I mean, whether it is a particle or not, in order to satisfy these phenomenological requirements.
Okay, so the first question, I think you would need to do, you need to understand sort of a micro level physics of the dark matter on small scales, which at the moment we've not looked into, but it's certainly a completely valid question, and I think it's very important. The second question I've forgotten. What was it again?
The second is whether throughout all of this approach, we can extract any hint about the nature of dark matter.
Right, so what you get is we're basically describing all the dark matter physics with a single quantity, the equation of state. You then need to try and figure out what does this imply for dark matter. And that's not something which is extremely clear how you would do. And I imagine there'd be quite a lot of degeneracies. The way the model is sort of leaning towards a negative value seems to imply interactions with dark energy, but what form of interaction is not clear. Perhaps a decay. But, yeah.
Thank you.
Any other questions? Okay, so let's thank Krishna again.